Yeah, I understand that a good number of you have a lab test today at 2 p.m. I'll try to take attendance earlier. And if we can finish a certain material, maybe we can call it a day earlier. We'll see how that goes. Let's review some quick announcement here, which is already on the e-class. Your programming test number 2 tomorrow. Don't worry about lab 3. Only worry about lab 2. Okay? You just need to worry about algorithm and also post-condition. For your written test number 2, the day remains unchanged. So you can look at the semester calendar just the same day, right? So we cannot really shift that by 1 week. And programming test 1, if you still want to speak to me, let me know, and we can talk. Written test 1 is there. There's no really a regrading procedure. So whenever you want to talk about your written test 1, you want me to go over the answer with you during the office hour, just drop by. You know, I think a good number of your fellow students already did that. So we can help you on that. That can be helpful for your final exam. And office hour, the same. TA contact information is the same. Okay, guys, any question? Okay, for your written test number 2, right? So the coverage is going to be, I'll confirm, but whatever we covered today is also going to be there. So you got exactly 1 week. But I'm going to release a guide and some example question, hopefully tomorrow or Friday the latest, so you can also get prepared. Okay, we'll see how much we can cover today. There's no rush. I think we got enough materials already. Just cover a little bit more. All right, quick recap. So what we got last time was we talked about this property. We corrected something about next states. So please make sure you corrected that on your notes as well. And then we talk about this property about parsing. And just remember, the first one there is something you would be expected to know. And the second one there is just optional, right? If you want to talk about ambiguity about grammar in general, feel free to drop by my office hour. We can talk about it. But you just need to know number 1. Okay. And we talk about this new pattern here about if, basically like an implication structure. We got some pattern over here. We got another pattern in the consequence, right? We spoke about you should really try to first draw the parse tree and then try to visualize exactly what it is supposed to mean. And for this case over here, you got a future operator in both the antecedents and the consequence. The important thing to remember when you study for this is the future point over here in the antecedents and the future point over here in the consequence, they are independent. They don't need to be the same, and it doesn't really matter which one happened first, right? So that's why we said each one of the 3 are allowed, is allowed. And we spoke about how to formulate it. I can see nested quantification is unavoidable. So when you study for written test number 2, you should also try to pay more attention about how the nested quantification can be understood, and also how we can prove versus disprove it. Right? That's also something we said earlier. And we did some example about this pattern here. You guys can take a look. Okay. And for exercise, I will try to maybe release the solution to all the exercises latest over the weekend. Okay, so you guys can still compare your answer. Okay. And we spoke about another pattern here, which will be GF as opposed to FG. So the easiest way to understand GF is it's like infinitely often. It is continuously the case, always the case. You can always find a future point. So for every state, you can find some future point. For every state, you can find some future point, right? That's the way to understand it. Right? And then you can look at the formulation here. All right, that's something we said last time. Let's review that very quickly, and then we can talk about proving it and disproving it very quickly. All right. So since we talk about model satisfaction, so we should start with a universal quantification, right? That's model satisfaction. And we got a global operator, so we should go global at the outer level. And also we got future operator, so we got inner level will be exist, right? And one thing that's very important, you can see the future point here is relative to the I over here. That means for every state of index I, you can always find a later future state, which is J. All right, so that's something you want to pay attention to when you look at the pattern. Any question about the formulation here? All right, good. So what I will do is let me now briefly talk about the proof, disproof, and then the 2 exercises. I'm going to do that today for sure. But before that, I will say we'll rather maybe do some example first so you can appreciate a little bit more how to understand the difference between different patterns. Let's now talk about proving and disproving first. Before that, any questions? All good? All right. All right, let's now talk about proving it and disproving it, right? To really prove it, since we talk about universal quantification, so if you want to prove it, you have to argue for every possible path starting with S, right? You got to argue, consider all the path patterns. Okay, let's now write it down. For number 1, you want to say consider all the path patterns. Consider all the path patterns. All right, and then once we handle all the path pattern, you want to say for every possible state in that particular path that we have chosen. Okay, so you can maybe make it a little bit easier for you. You can see say for all the path pattern, let's say pi. The pi is going to start with S, right? And then for number 2, let me say start over here. Okay, that's going to handle the middle level universal quantification. That one there, you're going to say consider all the states in pi. All the state, let's say S, right? You say S over here. In pi. You know what? Because we already got S over here, it can be a little bit confusing. Why don't I say T, right? Just the states, okay? Just avoid confusion. For all the states T in pi. And then finally, you have to handle for this particular existential quantification. That's the last one. You want to find a witness, basically, right? So number 3 will be, you want to find a witness. Find a witness. Stay at index J such that pi j satisfies phi. All right, so that's the 3 steps you got to watch out for. And of course, you can say here, let me draw a little bit more connection here. The T here is at index I. Right, so we got index I, and also we got index J. Okay, so I would say for the written test that's coming next Thursday, not this week, but next week, you want to really want to review all the formal definition for the operator that we spoke about, and also what it really means to really nest them, right? That's really something you want to focus on for next Thursday. How do we disprove it? To disprove universal quantification, you got to give a witness path. Okay, so let's start with that. So to really start with that, you have to give a witness path. Give a witness path. And let's say it's pi. All right. And then the middle level here is, again, a universal quantification. How do you disprove it? You want to give a witness states. And then for that one there is going to be number 2, you have to give a witness states at index I. Okay, for example, in pi, of course. Since we are trying to get related to the pi that we have chosen. And finally, how do we disprove existential? You want to show that relative to I, all the subsequent states is not going to satisfy phi. All right. So number 3 could be something a little bit trickier, so you definitely want to make sure you also review the basic disproof strategy for existential quantification. Okay, that'll be the last one. So you want to say all possible j such that j is subsequent to I, I'll say larger than or equal to I. It is the case that pi to the power of j does not satisfy phi. All right. If the definition is still going to bother you, that's maybe something you want to focus on more, when you review. Okay. So proving versus disproving. All right. Any part that's not clear to you before we do some example? All right. Good. Okay. Let's do some example. Okay. Especially the infinitely often, right? GF. And just don't forget, it's called infinitely often. Okay. Okay, let me just make sure. Okay, I'm good. Okay, let's now do the first exercise over here. And let's start with something simple. So we're doing path satisfaction. We're going to consider all the paths starting from S0. starting from S0, is it always the case that it's infinitely often P is true? Anyone? If you don't think so, you should really give me a witness path. Farris, go ahead.
No.
Give me a witness then.
S0, S2, S2, S2.
And how come that one would contradicts this property here?
Because S2 does not satisfy P.
Yep, exactly, right? The idea would be, think about intuitively. In here, yes, you satisfy P. However, once you get there, you can never find a future state anymore that will satisfy P. All right? Think about it more intuitively. So what Farris said is exactly right. So this will be false. And you just want to give a witness path. Let's say S0 and then S2, S2. Okay. So you can think, I'll give you two explanations over here. Okay. You can say that starting from S2, there is no future point. That satisfies P. Okay, that's one way to say that. Or another way to say that would be, you can say, if I try to say I want to get all the paths starting from S2, there's actually only one path because you get stuck there already. This one here is simply going to satisfy globally true, not P. There's another way to say that. To say that if you consider all the paths starting from S2, there is no way for you to satisfy P. So infinitely often cannot be true. Right? Because S2 is actually part of that path. Okay. If you prefer one, it's definitely fine. It's acceptable. Okay. All right, let's now do one more. How about this one here? Infinitely often P or Q. If you don't think so, again, give me a witness path. Anybody?
S0, S2, S2.
Yeah, again, yeah. So I think that these two examples are rather trivial. I wouldn't say trivial, rather simple. I just want to get some feel about this infinitely often, right? Yeah, if you try this one here, you can see once you get there, you just have no way to establish either Q, P or Q because only R is true, right? All right, so for the same reason. So this one here is also false, right? I'm just going to write down the same witness path. And then you say S0, S2, and S2, etc. Okay? You can think about from this point onwards, you simply got not the case, P or Q. Simply, it's not going to be satisfied. Okay? All right, not too bad. And let's now do another one. Okay, just to, this one also help us do one of the exercises. Okay, let's say we still consider S0. Okay, so I would say S0 over here, and then it's model satisfaction. And then I would say GF, P or R. John? That one's a model satisfaction.
Even S0, S0, right?
Yeah, that's S0, yes, S0.
The one we just did on the book before, that was the model satisfaction.
You mean this one here?
Yeah.
It is model satisfaction, yes, because you have a state here, right? But if I put a path, it will be path satisfaction, yes. All right, guys, how about this one here? True or false? True? How would you argue about it?
Okay, so basically if you go towards the path S0, S1, S0, you still have the variable P and or
Mhm.
R
Yep.
present in the path. If you go to the path from S0 to S2, you still have the variable R.
Yeah, yeah. You definitely can actually go for each of the pattern, to actually argue that for each pattern there, you will get infinitely often P or R. That's definitely one valid approach. But I want to show to you this one here is interesting. Somehow P or R is going to be satisfied by all the reachable states. You can see this one satisfies P already, this one satisfies R, this one satisfies R. All the states satisfied. So what I can claim is something that turned out to be even stronger. All right. So what I can say is, in fact, well, first of all, the result should be true. Okay, so that's the answer. But I can say, in fact, S0, the same starting states, model satisfaction, G, P, or R. Right? So that's something we did a little bit earlier in the lecture. So if I only got global operator, I'm saying that for all the reachable states, or all the paths, it's going to satisfy this P or R. That's actually true. Right? If I know that this is already true, this one here is a no-brainer. Whereas a no-brainer is logically implied by that. Okay? So what we'll get, actually that's one of the exercises, but that's okay. I think we can just show that by example. So there is a property over here. You guys can just note over here. If I know that it is globally true, some property, okay, then it must be that it is infinitely often that property is also true. However, not vice versa. Exactly why not vice versa, when we get to that exercise, I'll show to you. Okay? It's very easy to visualize it. Okay? I'll say not vice versa. Not vice versa, to be more explicit, if you know that it's infinitely often some property is true, you cannot say that in tails is globally true. You cannot do that. All right? All right, that's the first example. Okay, let's now do the second example. Okay, right here. And let's take a look at this one here. Okay, I'll give you some time to actually think about at least what this satisfaction is trying to do. It's like an implication. We're saying that if infinitely often P, then infinitely often R. That's what I'm saying. It's an implication, so there are many ways for you to, there are different ways for you to show. If you're able to show that, for example, maybe the antecedent is false, you got it. Or if you're able to just show that the consequence is actually true, you also got it. But I'm going to show you another way, which will be true implies true. Right? That's another way to show that. Okay. Okay, let me just mention that, right? So let me just remind you very quickly. Okay. So for implication, let's remind ourselves, you can try, you may try. First of all, you can say false implies anything if you're able to show that this is false. Okay? But if you're not able to, of course, it's a dead end. Or if you can somehow show that the consequence over here is simply true, that'll be fine too. Okay? So these two you can definitely give a try. But I'm going to show you the third possibility. True implies true. And it's called assuming the antecedents. I think you guys heard about this proof technique, maybe back in the 1090 or 1019. Okay. So I'm going to show to you as follows. Okay. Let's say assume the antecedents. In which case, let's say infinitely often P is actually true. What do I mean I assume it? That means I only care those paths where infinitely often P is actually true. For those paths that do not really have this property about infinitely often P, I simply don't care. Right? That's assuming the antecedents. So if I assume this particular property here, which path or paths should I consider? Infinitely often P. Only here, right? Because whenever I get to S2 from here or to here, S2 itself, there's no way to satisfy P. All right? Okay. So this one here, that tells me only need to consider S0, S1, S0, S1. That means we never go to S2. We never. All right? So now we have constrained ourselves into this path only because we assume the antecedents. Now we can think about whether the consequence is going to be satisfied on this particular path. Is it? Is it the case that infinitely often we got R? Indeed. Because for that path there, you always get alternating into S1. So infinitely often you will get R true. Doesn't need to be every state. As long as infinitely often, you are fine. All right. So now you can say number 2, you want to argue in this path, which is S0, S1, S0, S1, the consequence is actually true. Because if you look at that, S1 over here always is going to satisfy R. So you will get infinitely often into S1. And all these is going to satisfy R. Okay, so that'll be enough. You want to show infinitely often. Yeah, so I think if you go back to the strategy that we spoke about last time about infinitely often, so you actually see about proving implication, right? So you will see that one of the strategy is about proving true implies true. So this is just one example of that. Okay. All right, one more example. How about this one here? True or false? We say infinitely often R implies infinitely often P. If you don't believe that's true, give me a witness path. Barrett? Yeah. Yeah, that seems to be a very popular path to guess, right? Okay, good. But don't forget, in the written test or exam, I may not give you the same graph, right? So that's good. All right. All right, this one here is actually false. Okay. So witness path. S0, S2, S0, S2. All right. Because this path here, once you get to S0, S2, you just get stuck over here. And then let me make it more explicit. You basically got this one here, and then you simply got stuck right here. So once you get there, you can see for all the states, infinitely often R is definitely true. Absolutely, so that's true. However, you never get a chance to satisfy P, no way. So that will be false, right? So for that one there, so especially for this one over here, you can say that infinitely often R is true. But infinitely often P is false. So we actually got true implies false, which is equivalent to false. All right, that's a justification. Yeah? Yeah, I agree. Yes, absolutely. Sorry. Yeah, I definitely agree. Thank you. Yes. All right, guys, any question? John?
If they get much more complex, then we can move the path into each of them, right? So like S0 satisfies GFR and S0 satisfies GFP. Like if they get much more complicated on either of the sides.
Say it again. Are you talking still about the same property
It
here?
doesn't matter, but like as they get really complicated, we can then move them into like either sides of the implication, right?
Mm-hmm.
S0 satisfies left and S0 satisfies.
Yeah, exactly. So here I'm just trying to go a little bit more like a shortcut, right? So yeah, so there are different ways for you to prove logically. So in the exam, we'll definitely judge to see how valid your argument is. Yeah, for sure. All right. Okay, I would suggest we do the 2 exercises and then we'll see how the time goes. All right. All right. Question, Barris.
For the top one, you only need to argue for the one path, like
You mean
assuming the antecedents, you don't need to argue for the ones that.
exactly. So you think about what assuming the antecedent really means. If you assume this one to be true, that means anything that's actually false, you get false implies anything equivalent true anyway. So here we're assuming that infinitely often P is true. So then that means we only consider those paths that's going to make the antecedent true, and then concentrate on that.
Okay.
Mm-hmm. Okay. Guys, are we okay with the example here? Okay, good. Okay, let's talk about 2 exercises. Okay, and then we'll see how that goes. All right, exercise number 1. All right. So now you're given 3 choices, right? We're basically comparing GF and G. Actually, that's something we just did, right? So now you should be more in a better position to choose. Option 1, 2, or 3. Anyone? Besides Adrian, okay, I'm pretty sure you know the answer. Give it a try. Option 2, okay. So when you say this one here, that's correct, okay. You're basically saying this is a stronger property, meaning that it would be more difficult to satisfy this than this. All right, that's good. All right. All right, so that's the correct answer. Okay. So let's visualize this, and I'll give you one another important diagram. Okay. So if you think about, let's say, we'll put it here. If you think about G over here, G5, we are basically saying every state on the path towards infinity have to satisfy the phi. You cannot miss any states. As long as you miss the state, there will be a witness path to show that it's false. On the other hand, if you actually got GF, infinitely often phi, it would be acceptable. For example, you can say every other states. I actually got the phi satisfied. Why would this be okay for GF phi? Because for this state over here, this will be the future point. For this state here, this will be the future point. For this state here, this will be the future point, and etc. Right? So infinitely often is fine. So now here comes the important diagram. You really want to be able to kind of visualize yourself, right? Since we say this one is stronger, strictly stronger, so you must be able to draw things like this. Stronger, it should be a strictly smaller set of model that's going to satisfy this property. So I'm going to put G phi over here, okay? Strictly smaller. And then the GF phi is going to be right here. All right? That's all good, but you ought to know if this is a strictly smaller set than this one here, there's got to be a member model over here that's going to satisfy this, but not that. You want to know what exactly it is. That might be something I'm going to ask you in the test, right? And that one there basically is something that satisfies G of, is going to be infinitely often. However, it is not globally true. Okay? That's exactly here, right? You can see this one here is infinitely often, but this one here does not satisfy G5. Okay? And the same model here, the G5 is not true. Okay, so you can link this one over here to this one over here. Okay. Let me recap very quickly. Okay. So we're basically choosing which one is strictly stronger. So you want to be able to visualize each one of them to see why it is the case. And then when you try to visualize them in this kind of diagram here to show the relative, which one is stronger, which one is weaker, then you also need to choose a member that's going to satisfy one but not the other. Right? You want to know what exactly it is. Right? We got one more example to really do this diagram. Okay, another one. All right, let's do one more. How about this one here? This one here, just before I point to Adrian, okay, or any others, we're basically having FG versus GF. I'll give everybody some moment to think about. This one here is saying that at some future point, it is globally true or continuously true, phi. This one is saying infinitely often, the phi is true. Now we want to know which one is actually stronger, or they are just equivalent. Guys, think about it. This one is actually the trickiest one that we have to deal with so far. You think it should be 1? Okay. Let's say we go with your thoughts over here. Let's say, let me not say yet whether it's correct or not. If you believe this one here should be stronger, okay? So you're saying that at some future state globally, phi. And then this one over here, strictly larger, that's weaker. Right? If you believe that's the case, then you gotta be able to find some model over here that is going to satisfy G of phi, but not the case FG phi. Are you able to describe what that witness should be? If you're able to, then it sounds like a right answer. If you cannot, then we'll be a little bit hesitant, right? Are you able to?
Well, GF means eventually you're going to see a recurring pattern.
No, you're talking about FG. GF, you kind of did the wrong order. If you look at here, that's good. So here you can say GF, we are saying that continuously, there's always a future point. So it's infinitely often. And this one is saying at some future point, continuously. Right? So they're different. Okay, that's okay. Adrian?
The path which alternates between satisfying and not satisfying phi will be in GF but not F.
So you also agree with a fellow student, it should be 1. Okay? Anyone else? Sounds pretty accurate. Good. Okay, nice. Yeah, I'm going to give you guys an answer and justification. You guys can think about it, right? It takes some time. So this one here, yes, it should be this one here. Okay? And for this particular witness here, that's going to satisfy one, but not the other. Let's see exactly how this can happen. Okay? I'm going to give you one pattern where infinitely often is going to be true. As Adrian correctly said, why don't we say alternating satisfaction? Okay, so let's say the first state here, phi is true. The second state, phi is not true. And then phi is true, and then phi is not true. And phi is true, not true, etc. This one here definitely satisfy GF phi. We say that infinitely often we got phi satisfied. Doesn't need to be continuously. But apparently, that one there, does there exist any future states? That's globally true. Not really, because any future state you choose there is guaranteed either the next states or the next states will fail that, since we assume alternating state being satisfied, right? Okay, so here we're saying that phi is satisfied in every other states. And if that's the case, we know that GF phi definitely is going to be satisfied. You can always find the future states, always. However, since it's every other state, that means every other state phi is also not satisfied. In that way, globally true, cannot find any future point for that. Okay? So that means FG, there is no such future point. Okay, like that. Guys, any questions? Yeah. Okay, if that's good for you, let's see where we are. Okay, on the slides. Okay. Yeah, if you look at the slides right here, you can see we are basically, we are now until slide 45. Okay. For LTL, there are 2 more topics I would like to cover. One would be about the 3 more operators, but they can be understood somehow using global and also future operator until, weak until, and also release. Okay, we're going to talk about the formal definition and do some example. And then the final bit about LTL is to somehow see how we can use the different operator to really formulate some real life example. That's something we'll do. Okay, but I think it might be nice to maybe pause over here as a logical chunk. Okay, and then this will be where you're going to cover until for written test number 2. All right, so I can now confirm for your written test number 2 is going to cover until slide 45. Okay, up to here. Okay, so the plan will be next Monday we're going to finish the final 2 bits about the LTL. Next Monday, and then after that we'll do the remaining 3 classes. We're going to do program verification. So I think for CTL we don't need to worry about. Okay, guys, any questions?
Professor, for written test 2, it will be cumulative
That one there, let me confirm a little bit later. Yeah, but I think definitely I'll cover until and including slide 45. Yeah, but I think it's going to be mainly about LTL. Maybe not the parse tree part. Okay, maybe just the semantics part. Okay, I'll confirm the coverage. Okay, if you guys don't mind, why don't we say, since your fellow student got some lab tests today, why don't we say we take attendance and then that'll be it. And then we'll finish off the LTL next time. Any objection? All right, that's good. Let's take attendance then.